All right, welcome. In this video, we're going to continue practicing evaluating integrals. So here we're going to evaluate the integral from 1 over root 2 to 1 of 4 divided by the square root of 1 minus y squared with respect to y. So that's dy. And then it'll be helpful to remember this. And this is from the table from an earlier video. And hopefully that's helpful. So I can see that the antiderivative of 1 minus x squared in the denominator within a square root is equal to sine inverse of x plus a constant. So that's going to be really helpful. So let's go ahead and use this. So that means I have 4 times the integral of 1 over root 2 to 1 of 1 over the square root of 1 minus y squared dy. All I did was rewrite it so that the constant of 4 was on the outside of the integration here. And so I end up with 4 times a sine inverse of x from 1 over root 2 to 1. Okay, so now let's evaluate. And for this, we're going to have to do a little remembering back to trig. So if you recall, sine inverse of y equals some angle, and this is if and only if, so this is bidirectional, sine theta equals y. So what does that mean? Well, if I draw this little graph here, and let's go ahead and draw just our sine function. So if you remember graphing sine, if we want to find its inverse, it's not 1 to 1. So we actually have to restrict sine from negative pi over 2 to pi over 2, and that's inclusive. So if we translate that to the unit circle, that means when we find angles for sine, we're only looking at this section here. So that's quadrants 1 and quadrant 4, and we're going to include these endpoints. So this is negative pi over 2 to pi over 2. So now if we look at this y here, when we plug something in for sine, we're going to get an angle. So what this is telling us, and let me write out the next step, and I'll leave the 4 here. So let's do the calculus part. So applying the fundamental theorem of calculus, I have sine inverse of 1 minus sine inverse of 1 over root 2. And if it helps, 1 over root 2 is equal to root 2 over 2. Maybe that's how you've seen it before, so I'll rewrite this really quickly. Okay, so now let's go back here. So what this is telling us, if I have a particular angle within quadrant 1 and quadrant 4 here, so just in these two quadrants, so where is sine of theta equal to 1? That's the first question. So sine of theta is equal to 1 right here at pi over 2. So I have 4 times pi over 2. Now let's examine where is sine of some angle equal to root 2 over 2. That is, sine inverse of root 2 over 2 will point me to the angle where the sine of that angle, that is the y value, the vertical value up and down on the unit circle, is equal to root 2 over 2. And that happens here at pi over 4. So let's write that down in its own color as well. So sine of theta, where is that equal to root 2 over 2? So theta equals pi over 4. So I end up with pi over 2 minus pi over 4. So this is just 4 times pi over 4, or just pi. That means the value of this definite integral here is just pi. And again, a definite integral gives us just a number. All right, as you can see here, we have the graph of f of x equals 4 divided by the square root of 1 minus x squared. And now let's see if our integration process was correct. And if you're asking yourself right now, why is this an x when our integral was an y? That is a limitation of the technology. The way GeoGebra works, we need to graph things in terms of x if we plan to find an integral. Okay, so you can do this at home too. Just type in the word integral here into the bar. And then f, comma, 1 divided by the square root of 2. And then comma 1. And if you notice, we get 3.14. So we get the same answer we got, which was pi. So what you have just seen, and actually let me adjust this graph because it seems like our area is going up in this direction and I want to see it all. So the area here from root 2 over 2 to 1 under this curve is just 3.14. Next, let's take a look at this indefinite integral. So unlike our previous example where we had a definite integral, we will not end up with a number. We'll end up with some function plus a constant. Okay, so let's rewrite this first, because right now sine theta, cosine theta doesn't remind me of any nice trig function that I know with an antiderivative. So I'm going to rewrite this as sine theta over cosine theta times cosine theta d theta. So this is the same thing as sine theta over cosine theta times 1 over cosine theta d theta. So I have the integral of tangent theta times secant theta d theta. Well, if you recall, the derivative with respect to theta of secant theta equals tangent theta secant theta. And you can also write this as secant theta tangent theta, since multiplication is commutative. It doesn't matter what order we write them in, so these can be swapped. All right, so that tells me that my integral here is just equal to secant theta plus my constant, since I have an indefinite integral. That's it for this video. I hope this was helpful.